Hello, everyone. Let's start. Today, we will talk about a latch and a flip-flop. So these are two very important circuit component which can help you to store some data. So they are just a temporal storage for your data. Because they are very fast, so they can be used inside a computing unit. Typically, you can use them to implement register, particularly the pipeline register, so that you can use them to store some temporal data between two pipeline stages. So these are three basic logic gates. You can see we have a NOT and OR gates here. These are their truth table. And these are the function. There are some pseudocode. If you want to write some VHDL, you can use these languages. And but these three data are just some combinational logic, which means that if you apply your inputs A and B on the input, you can get your output immediately, maybe after several picoseconds. So we can view it as immediately you can get your data. So there is no clock concept. We need some stateful component which can help you to record something. Before that, we only have a combinational logic. Output is computed when the input are applied. System has no internal state, so there's no clock, there's no finite state machine, only very simple gates. So nothing computed in the present can be dependent on what happened in the past. So you can, in summary, you can only compute one step. This is the a summary for the combinational logic. You have all the inputs here and you have output here. When you apply your input, you get your output immediately, no matter how many input you have or how many output you have. So we need a way method to record some data. We need a method to build some states so that we can have some stateful circuits. We need some state holding devices so that eventually we can have a finite state machine. So in this lecture, we will talk about the latch and the flip-flop. There are multiple types of latch and flip-flops. The simplest one is a D-latch and the D flip-flop. For example, we can use D-latch to implement registers. It need to record multiple bits, not only one bit, but at least 1 byte maybe. And then we also need a decoder and an encoder to support these registers. Eventually, we can have a so-called finite state machine, which we can design logic circuits with some states if we have a finite state machine. We will introduce a Mealy machine and Moore machine. They have different hardware cost and different power consumption, but they can implement the same function. Some example is a serial adder and a serial multiplier. We talked about a carry ripple adder before. It's a parallel adder, but now if we have a finite state machine, we can record the intermediate results from a last cycle. In this way, we can, if we have a finite machine, we can use the the previous result from the last cycle to do the current computation, so that we can implement some serial adder, which apparently have less hardware cost. So let's talk about the D-latch. Here is one example. It's not exactly the D-latch, but it's a part of the D-latch. So this is an inverter. Assume that we store 1 here. Because this is an inverter, if I apply the 1 on the input, I will have a 0 here as the output. So because these two are connected, so I have a 0 here. For this inverter, the input is a 0. If I apply this 0 here, I have a 1 here. So these two are connected, so they are the same. This is good. And you can see that when I connect two inverter together, I mean, I connect the output of one inverter to the input of the other one, I can somehow get a stable, so-called stable state if I store 1 here. But how about I store 0 here? If I have a 0 here, this is 1, this is 1, and this is 0. It's also a stable state too. So if I have this structure, I can somehow hold a 0 or hold a 1. So this is the basic element which you can use it as a storage. And then we will use that 2 inverter to build a simple memory. The simple memory is what we want to have here is that we store some data in the memory, and then we can read the data out of this memory. If we don't read the data, the memory can hold the data, can temporarily store the data. So this is so-called store. And the memory should also have another function, which is a load, which means that we write a new value into the memory. This is load. Basically, these two, the basic function of a memory element. And this is so-called a D-latch. Because the input here is a D, so we call it a D-latch. Q here is the output. We write the data into memory element from here, from the D input. And we can read some data, the data stored in this element from the Q port. So this is the schematic view of the D-latch. We have also a clock signal here. We also have a clock signal here too. So basically, they are the same. We connect these 2 points to the same clock. The difference between them is this is clock, but this is clock bar. So if we have a schematic view like this, here the clock is a 0, clock is a low. Why? Because this is open. When the clock is a 0, this switch is open, this transistor is open, but this bar is closed. When I have a clock as a low, you have 2 inverter connected together. It can hold the data. So this state is a so-called hold. What if the clock is open? I'm sorry. What if clock is high? When the clock is high, this is closed. This is open. So these two are not connected. And we only have a two inverter connected like this. And then this D can stored here, can be stored here, and can be also passed to here too, because here is a combinational logic. We only have two inverters here. We actually stored, because this is an inverter, we actually stored a D bar here, but a D here. Why? Because I apply another bar on the D bar. Based on the negation law, I have a D here. So the output here is a D. When the clock is high, we have a load operation. Any question? So by two simple inverter, we can implement a so-called stateful device, which is the D latch. With two additional switch, we can implement the hold function. When I close this switch, but I open this switch, I have a connected loop here. So this is a hold. But if I open this, close this, this is a load operation. The D can be passed through two inverters and send the output D here. But I also have a D bar here. So the control can be done by a clock signal. Clock signal can be performed like this. So when the clock is low, like this, the D latch just hold. But when the clock is high, the D latch can load. So when we have this, so this is transparent. Transparent means just load. When we have a D latch, what can we do? We can do some computation here. And then this D latch will load the value here during this half cycle. And then the D latch will store a square symbol, for example, a square symbol. But I can do a new computing here. And then this D latch will load this circle to here. I will do another triangle computing, and then the D latch can help me to store my triangle here. So with this D latch, I can store my data. I can do new computation by some adders. For example, let's say adders. And the adders can also use the content in the D latch as the new input for the second cycle. So this square can be used by the computation of this circle. Or it cannot, or you can either use or not use, depend on your application's need. But we just figure out a way to store the data. So let's see some waveform of the D latch. We have a clock here, and we have the input like this. So back to here, when the clock is low, it's just hold. When the clock is high, it's transparent. So when the clock is high, this is a high. It's a transparent. The transparent means your output is exactly the same as your input. Your output is exactly the same as your output. Okay, this is so-called transparent. However, when the clock is low, it just hold. Hold means I just hold the state which my last cycle, which obtained during my last cycle, which achieved by my last cycle. Because my last cycle, my previous cycle, on my last cycle, this is 1, so it just hold this one. This is 0, it's just hold this 0. Again, this is 1, it's just hold 1. So if the clock is high, you can change anything you want, and you can even change inside this half cycle. See this? You can even have some waveform like this. You can change during this half cycle. But when the clock is low, you cannot change it. Just hold the value from the previous cycle. Any question? This is actually not good because you can change all the stuff here during when the clock is high. If you have some noise, easily the circuit will be influenced by those noise. The result will be destroyed by the noise. So sometimes you don't like this characteristic, which when the clock is high, you can change anything you want. Sometimes you just need to, change once. But at least the D latch is the first storage element for you. So by the D latch, we can implement something new. For example, accumulator. By a carry ripple adder, you cannot implement a accumulator by only one adder. What you can do is just statically, have maybe 2 adder so that you can accumulate the 2 results. If you want to accumulate an n result, you need an n adder. If you don't have latch. On the contrary, if you do have latch here, you can just use one adder. In one cycle, you can do one accumulation. You can read the data from this latch and do a new accumulation, accumulate, the new results, the new input to the original values here. So in this way, you can achieve accumulator by only one adder here. Again, if when the clock is high, you have some radiation from some universe space, so that your latch is accidentally flipped from 0 to 1. Then the result will be wrong. For example, you have some noise and the result will be wrong because when the clock is high, the latch just change with the input. The latch output just change with the input like this. So in this way, we want to have a more reliable storage devices like the LAN, like the flip-flop. The flip-flop is also very simple. We just connect 2 D-latch together. And we use also one single clock to control them. This D-latch is controlled by clock bar, but this one is controlled by clock itself. So when the clock is low, this clock is high. When this clock is high, you can load. But for this clock, this is low. It's just a hold. When the clock is high, this is load. This is hold. So somehow you use this D latch as a protection for the second one. We will talk more in this slide. You can see here when the clock is low, this is low, this is high. If this is high, this is transparent. This is a hold. If I write a 1 here, this is 1. But this one can still hold the 0 from the previous cycle. And then this clock changed from 0 to 1. When the clock is at 1, this is 0. This is low, and this is high. When this clock is low, it's just hold. It hold what? Hold the value from previous cycle, which is 1. So I have a high here. And then this is transparent. This high will be passed through this gate to here. This is 1. So in this way, I just load the 1 I write here to this D latch and then to this D latch. Eventually, I get the 1 here from the output. So you can see that the output is changed on this edge. When this clock changed from 0 to 1, I can receive the 1 I write to the input. So this D flip-flop is triggered by this edge, not the level. For the D latch, everything is triggered by the clock level. Whether it's high or low, if it's low, it's just hold. If the clock is high, you can load anything you want. And the output will change with your input. Everything triggered by the level, clock level. On the contrary, the D flip-flop here is triggered by the edge. It actually do not care about the voltage of the clock. But no matter it's a 1 or 0, it doesn't matter. But this flip-flop is sensitive to the change of the clock. When the clock changes from 0 to 1, the flip-flop will change. Also, when the clock changes from 1 to 0, the D latch also will be changed. So it's triggered by the edge. So in this way, if I put a flip-flop here, it's more reliable because each time the output of the flip-flop will only change once during the entire cycle. So in this way, if I have some noise, it doesn't matter. Even the noise flip the content in this flip-flop, I can still hold the original value. So the D flip-flop is more resilient to the errors, to the noise. So this is the waveform of a D flip-flop. So you can see we have a clock here and we have the input as D here. And then everything is actually only triggered by the rising edge. So the D flip-flop only sensitive when the clock changes from 0 to 1. So only 3 time point the D flip-flop is triggered. So you can see that the output here for the D the output for the D flip-flop here is changed at this point from 0 to 1. Why? Because the input here is 1. Also, it will be changed here. Why? Because the input here is a 0. I'm sorry, this is the D flip-flop results. It changed from 0 to 1 here and from 1 to 0 here. And then the input is still 0, so the output is still 0. The last row is the result for the D latch. You can see this is the, by comparing these two waveforms, you can see the difference. So the D latch just change when the clock level is high. It just change with the input. So now you can see the difference. So when the clock is high, it just change with the input like this. So if this is a noise, an error, then D flip-flop can tolerate this error. But if you use D latch, then you may have some mistake here. And of course, the error tolerance is coming from the hardware, higher hardware you pay, because now you use two D latches as one single flip-flop here. And in this example, we only show that the D flip-flop is triggered by the rising edge. This is the rising edge. Can you make it triggered by or sensitive to the falling edge? Yes, you can. You just simply add some inverter. That's good enough. Are there any storage element which is sensitive to both the rising edge and the falling edge? The answer is yes, because now the DRAM you are using now is the so-called DDR, double data rate. How they achieve double data rate? They just try to fully utilize the clock cycle here. They try to utilize both the rising edge and the falling edge. So this figure summarizes more about the difference between the D latch and the D flip-flop. This is the flip-flop. This is latch when the clock is high. The D latch is sensitive to the clock level. When it's high, it just changes with the input here. But the D flip-flop is only sensitive to the rising edge, and the rising edge. So this is the difference, major difference between the flip-flop and the latch. And you can also make them sensitive to the falling edge here. Again, I explained that you can try to use these period to store the data you compute in the pure half cycle or pure cycle, so that you can compute something and then store in the D latch or D flip-flop, and then compute some new stuff and store the data in the same D latch or the same D flip-flop. So it's just a more high-level accumulator. The accumulator is a very good example to explain that. You need to do the addition. You also need to store the temporal intermediate accumulated result to some buffer, like D latch, D flip-flop, and accumulate a new element to the intermediate results. So these are the summary for the D flip-flop and the D latch. Any question? So I post. Yes.
I figured it sounds like you're about to talk about the project. I had a question about homework too, depending on when you want to talk about that.
Good. So Yeah, you can start.
Okay, so I implemented the adders and subtractors as described in the assignment. And then for the 1-bit adder, for the test bench, I did an exhaustive test bench because it's pretty easy for 8 states. But for the other adders and subtractors, there was an example binary additions and subtractions. So for the test bench, do we only need to implement those?
Yes.
Okay.
You don't need to cover all the cases. You just give me some example to prove that your adder can work. That's all.
Okay, thank you.
I had a question about the overflow detection. So what is expected? So I know like if the last output has a value, that means it's
you just send in a example to show that your
okay, I see.
Your
Okay.
adder can actually detect the overflow.
Okay.
You don't need to cover all the cases. You just give me one case. That's good enough.
Okay, I see. All right, thank you.
I post a presentation requirement here. Please use this week to form a group and select a topic. I believe you can change this topic in the future if you like. But again, you cannot change the group member. Keep the group size smaller than 3. So only 1 person or 2 persons in one group. And then you can try to list all these items in your presentation slides. We will do the presentation for each group in next week in the lecture time. Each group may have 15 minutes. And you can make a video for that. Or you can do an in-person presentation. I believe these requirements are very basic. You just introduce some group member. So the problem you try to accelerate. And try to define your problem, why this problem is important, and what's your plan, and what's your schedule, and what's your evaluation plan. Any question about this? I mean, you can read this after this class. If you have more questions, we can talk about on Wednesday in the next lecture. Or you can even email me. Any question about the homework, the presentation, please email me, okay? So we can stop today. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.